Today, we're tearing down a drone, not with a screwdriver, but with information. We're going to look past the propellers and the frame to get to the real core of how these things fly. The software, the control system, what I like to call its digital heart.
I mean, think about it. How does a little quadcopter just hang there in the air, totally still, even when a gust of wind hits it? Or how does it pull off a perfect, snappy flip and then just stop? It feels like it's got to be magic, right? Well, it's not. It's actually a really cool mix of physics and some incredibly fast computer processing. And we're going to pull back the curtain on exactly how it works. All right, here's our game plan. We're going on a little builder's journey. First, we'll look at the drone's body, its physical blueprint. Then we'll get into the digital brain. After that, we'll uncover the real secret sauce to its stability. And finally, we'll see how you actually take command and tell it what to do.
Okay, first things first. Before you can even think about writing code or flipping switches, you have to understand the physical machine you're working with. The software, the brain, needs to know the exact shape and layout of the drone to have any hope of controlling it. So, the one you've seen a million times is the Quad X. 4 motors, X shape, it's pretty much the industry standard, and for good reason. But then you see these bigger rigs, right? Hexacopters with 6 motors, or even giant octocopters with 8. They're for lifting heavy cameras and gear. But the real game changer with more motors is something called redundancy. Think about it. If a quadcopter loses one motor, it's coming down. But with a hex or an octo, it can often lose a motor and still manage to land safely. Pretty important stuff.
So, here's a classic question. Why doesn't a drone just spin around in a circle the second it lifts off? The secret is so simple, but it's brilliant. The motors spin in opposite directions. You see how the front left and back right spin clockwise? Well, the other two, the front right and back left, spin counterclockwise. This setup cancels out the rotational force, what physicists call torque. Every motor creates a twisting force, but by pairing them up like this, their twists cancel each other out and the drone stays pointed exactly where you want it.
Okay, so we understand the body. Now it's time to move on to the brain. This is where we stop talking about hardware and start talking about software, how we actually give the drone its marching orders.
You've basically got 2 main paths you can go down here. For almost everyone, especially drone racers or people who just want the best flight performance, you'll use a program with a nice graphical interface, like Betaflight. You just click buttons, move sliders, and toggle settings. But if you're a researcher, or you want the drone to fly a very specific mission all by itself, then you're going to be writing actual code in a language like Python or C++. So it's either tweaking settings or writing scripts. 2 different tools for totally different goals.
Getting everything set up is actually pretty easy. You grab the software, you run the installer, you know the drill. But listen up, do not just blow past step 3. Those drivers are absolutely crucial. They're like a universal translator that lets your computer speak the same language as the drone's flight controller. If you skip this step, nothing else is going to work. Seriously, don't skip it. So once the software is good to go, you got to make the connection. The old school, most reliable way is just to plug a USB cable right from your computer into the drone's flight controller. Simple. But some drones, like the little Tello for example, are pretty neat. They create their own Wi-Fi hotspot. You just connect your computer to that network and you can program it totally wirelessly.
And now we get to the heart of it all. This is the real magic we were talking about at the start. This is the secret that lets a drone hang in the air like it's frozen in time.
And that magic has a name. It's called the PID loop. I know, it sounds a little technical, but the idea is actually super intuitive. Imagine you're trying to balance on one foot. You're constantly making tiny adjustments, right? Leaning a little this way, a little that way. You feel yourself start to fall, and you instantly correct it. That's a PID loop. It's a system that is constantly looking for errors and then instantly fixing them. And a drone needs this because, believe it or not, it's an inherently unstable machine. It wants to flip over. The PID loop is what tames it.
So let's break down P, I, and D using that balancing analogy. P is for proportional. That's your immediate reaction. If you suddenly lurch to the right, P is the part that instantly shoves you back to the left. I is for integral. This handles those slow, creeping errors. Imagine a steady, gentle breeze is pushing over. I notices this buildup over time and tells you to lean into the wind just a little bit to stay balanced. And then there's D, derivative. This is the really clever part. It predicts the future. It sees how fast you're correcting and slows you down so you don't overshoot and start wobbling back and forth. It's what makes the corrections smooth.
And here's the part that just blows my mind. This whole process, sensing an error, calculating the P, I, and D correction, and sending a command to the motors, it doesn't happen once a second. It happens thousands of times, every single second.
It's this insanely fast blur of tiny adjustments that we see as perfectly smooth, stable flight.
So how does the PID loop even know it's tilted? Well, the brain needs senses, right? It needs eyes and ears. For the drone, that's the IMU, the inertial measurement unit. You can think of this little chip as the drone's inner ear. It's what gives it a sense of balance. It's constantly screaming at the flight controller, telling it which way is up, which way is down, and how fast it's rotating. The IMU provides all the data that the PID loop needs to do its job.
Okay, deep breath. We've got a physically sound drone, we've programmed its brain, and its PID loop is keeping it rock steady. Now for the really fun part, telling it how to fly. And you do that by picking a flight mode.
And here are the greatest hits. If you're just starting out, you're going to live in angle mode. You let go of the sticks, it levels itself out, it's a lifesaver. Ready to do flips and rolls? Then you got to graduate to acro mode, where the drone stays at whatever angle you put it in. Total control. For you photographers, altitude hold is amazing. It just locks the drone's height so you can focus on the shot. Position hold takes that a step further with GPS, locking it to an exact spot in the sky. And of course, the one we all hope we never need but are glad to have. Return to home, the ultimate safety button.
So, there you have it. From the way the motors are laid out to the thousands upon thousands of calculations firing off every second inside that PID loop, that is the digital heart of a drone. It's this incredible dance between hardware and software. So the only question left is, now that you know the secrets behind the flight, what are you going to build? What are you going to command it to do?